this is the quantity promised, right, that should have this conservation law, and this is the promise we know, the quantity we know has this conservation law, but we want to see what the relationship is. So we know we want to take the derivative, and so one way to do this is the following. I'm thinking that each of these things, bits, goes through a different channel with erasure probably epsilon I, right? And instead of taking here the total derivative, I take here the partial derivative with respect to each I. And at the end, all the epsilon I become, again, epsilon. And I have a 1 over n here, right? So that's the same thing. I just take partial derivatives here. And now I just need to work a little bit on that. So now just to make my life easier, let me just change things on the board. That's the advantage, okay? So let me write this now here as the following. By the change, this is a vector here, right? So I'm thinking of here xi, okay? And now then I have the second term, right? Will be the h of x tilde I, and then I have the same thing over there, and I have still this derivative and with respect to the epsilon I, and epsilon is epsilon I. Okay? Good. So let me just see. So far, okay, so far so good.
So using the chain rule?
Yes, yes. Okay, so far I've done it right.
Do you get an xi on the conditioning?
Yeah, sorry. That's exactly what I'm looking for here. So I have here the xi. Okay, so perfect. So then I need to write this, unfortunately, slightly more explicitly. So I have y tilde, let's say I, and then I have here yi of epsilon. Okay, good. So now, if you look at this part here, I give you already the position xi, right? And condition that I give you this, then the yi is simply that, or it's that erased, right? So, I can just forget about this part because I give you the xi, right? But now if you're looking at here, if I'm taking derivative with respect to epsilon I, the only thing that depended on epsilon I was that part here, right? All the other ones have some other epsilon j's here, right? So this actually has no dependence on epsilon I, so I can just get rid of the whole thing here. Okay, so far that's fine. So now I still want to work a little bit on this part here. So what did I want to do here? Let me see. Yeah, okay, so let me write this now here also a little bit differently. So let me write this here as y tilde I. Okay, and then I have still the yi of epsilon I here. Okay, so I'm just writing it, the rest thing that doesn't depend on it, plus this that actually depends on this thing. And so now let me look at this. Right, I have a conditioning here. So what can happen, right? So the yi epsilon I can either be equal to xi, right? And it's equal to xi with probability epsilon I bar, right? So if it wasn't erased, it's this. Or it's equal to a question mark, so it gives me no information, right? And that happens with probability epsilon I, right? So if I take this thing here now and I condition on the two cases I have, so I'm just looking at that before I take the derivative, right? So what happens if I see, let's say, this, if I see this guy here? Well, if I see this guy here, then I actually see the xi, right? And then the entropy is 0 because I have the entropy of xi, but I condition on xi, right? But if I see a question mark here, right, then this happens with probability epsilon I, and then simply this is gone and I have just left. So the claim is that this is the same as 1 over n, right? And so now I have just the sum, I is 1 to n of d of h of xi with respect to y twiddle I, okay, with respect to d epsilon I, and I have an epsilon I here, right outside. Okay, so this is simply this case here. Now, nothing in here depends on the epsilon I, right? These are all epsilon j's here. So the only dependence on epsilon I is this explicit linear dependence that I have here, right? So I can just get rid of this. Okay, that's my derivative here. And so this means this function here is just 1 over n times the sum over all positions here the conditional entropy on the ith bit here, seeing everything except the ith bit here, right? And so now I can think of that all these again go for a channel epsilon, right? I mean, I can set them all to be, so all of these go for a channel epsilon. And so now in general, for general channels, this would not be equal to this map decoder, okay? But so now we're using something specific for the BC. So first of all, this is just binary, okay? So there will be just some distribution, but it's more than that. The thing will be that for the erasure channel, either I can determine the bit exactly, so I have zero uncertainty, or if I cannot determine it, then then I have equal probability. So I'm using something that the code is linear here, okay? So I'm using the linearity of the code here, or it will be such that the distribution on the xi is the uniform one. Okay, so I'm using linearity here. And because of that, this entropy will either be 0 or will be 1. Okay? And so instead of now writing like this, that's exactly I can think of the indicator function that I can either decode or not decode, right? But that's exactly what I have here, right? I do the optimum decoder. It's mapped because that just corresponds to, I'm looking at the actual posterior distribution here, right? And I'm looking at the posterior distribution conditioned that I see everything of the vector except the actual position I. Okay? So I hope that you see that this is exactly equal to this decoder. So it has a very nice operational interpretation. Okay, so now just maybe 2 words about what about the general case. Okay, this is BC. For the general case up to some point, which I deleted somewhere, everything is exactly the same. So you also start again with the derivative of the conditional information. But at the end, it doesn't reduce quite as neatly as that. Okay, so the thing is slightly more complicated, has also an operational meaning as a particular decoder, but it's a more complicated function. For the spatially coupled story, everything still works out and it's fine, but I'm not going to mention what this function is because it's a little bit too long a story. Okay, but you can do this. So now what is the consequence of this, right? So the consequence of this is very simple, right? If we want, so first of all, if we do the general story now, where instead of, let's say, instead of the parameter epsilon, we're thinking of the entropy of the channel, so that's the general story, still goes from 0 to 1 because it's a binary channel, and we're plotting exactly this function here. Okay, let me just write it now as h. How did I write it? F of h, of the entropy. Okay, so then if I want a code or a sequence of codes to be capacity achieving, right? Then capacity here is exactly h star, which is 1 minus the rate, right? It has to be exactly at this point. And hence, the only way this exit function has to become a step function. Okay, so the only way that a code can become capacity achieving is if this exit function, or in general it's called a generalized exit function, becomes this step function. Now, from the derivation, in particular for the BC, that, it's completely trivial that we saw it, but there's something conceptually nice. How do you typically show that a code achieves capacity? Well, you would go up to the arbitrary close to the Shannon thing and show that the code has very low probability of error, right? So you can relate, this is essentially, it's equivalent essentially to probability of error. If this goes to 0, the standard bit error decoder goes to 0 and vice versa. Okay, or if you want to show that code doesn't achieve capacity, you would show that up here, it's still not, it's still at least takes on still a value here. With this area theorem, to some degree, you can show the opposite. Okay, so let's assume I wanted to show that the code does not achieve capacity. Okay, then what could I do? Instead of showing that here it is not, it's not very good. Okay, I could show that up here it's actually not very bad. Okay, because if I have something like this, okay, then I know, since this has to be error, I know that this has to go further down and has to come down at least here, right? And I can also do the opposite, right? So that's kind of, conceptually, that's kind of nice. And let me just give you one example, because Henri already did yesterday the iterative part of how to do this, right? So where this is quite useful. So think of the, I don't think Henri has explicitly done this, but might be implicit in what he did. So let's think of, let's say, an LR LDBC code, okay? Now you're all masters of LDBC codes because yesterday Henri talked about it, okay? So let's assume I wanted to show here that such a code does not achieve capacity, right? Let's say for the BC, just to make it simple. Well, how do I do it? What I will show you is that if I'm looking up here, so above capacity, that up here, I actually have some useful estimate of the bits. And since I have some useful estimates of the bits, I'm just even going to give you an upper bound. I'm still making it actually worse than the real best estimate that you can have. It cannot be that you achieve capacity. This curve, whatever the curve looks, it must go down further. Okay, so how do I do this? Well, whatever, let's assume I have transmission epsilon here, right? Then one way I can get an estimate of this bit. Okay, I'm not allowed to look at the bit itself, but I can look at its neighbors. Okay, can look at this and maybe this neighbor. So I can look at a neighborhood of size 1, right? And I don't see the bit itself, but I want to have an estimate of the bit, but I see these bits here, right? So I'm looking at a suboptimum estimate. Now, what will be the estimate for this? Well, if you work it out, it will be, it's this, okay? So the optimum estimate you can do about this bit, based on only the bits in neighborhood 1 down, just my nearest neighbors, right, is this, because the probability, this is an XOR, and the probability that, that I see some useful estimate here in the erasure channel is this, okay? This is the probability that I actually see a bit. If I see all the bits here, the r minus 1 bits, if I see all the bits, then I know what this estimate is. That's this, okay? And then I have L of these nodes here, L of these incoming. If any of them gives me an estimate, I'm done, okay? So I can show that this estimate up here is at least as good as this, okay? And if you integrate this now from some epsilon star to 1, and you choose it in such a way that this is equal to the rate, okay, and figure out what the epsilon star will have to be, you will find out that this epsilon star is whatever, is not a half, okay, so, sorry, I'm always talking about the rate a half, so this should be, the rate is L over R. So if I do this for LR being, let's say, the 3/6 code, where the rate is a half, then I would get, for example, here, I get here, for example, bound of 0.4915, okay, which is less than a half. So just by this, I showed you that this does not achieve capacity. And now, I can do this slightly smarter. Why don't I do this after 2 iterations, right? If I think of infinite, and if I actually go down and think of many iterations, I'll get a bound of 0.48815. Okay, so I get a better bound, and it turns out, but that's a much longer story related to spatial coupling that Henri told you. It turns out that actually is the exact map bound for this code. Okay, one can prove that by going to spatial coupling, showing that they have the same map threshold. That's a longer story. Okay, but you see that this very trivial thing here, in principle, gives us already the right bound. Okay, by just plugging it. So that's quite useful. Okay, so now let me get to the actual story. Okay, because I don't have much left. So let's see. So now, as I said, you could now take this idea and apply it to spatial coupled codes, and it would be a different proof than what Henri has told you about. But since I think also Nicholas will talk about some aspects of spatial coupling, I don't know exactly what, but I don't talk about that. So let me talk about codes with sufficient symmetries. And as I said, that's this joint work with Henri, his student Santosh Kumar, Marco, whom I'm missing, Srinivas, and Aaron Sasoglu. Okay, so I'm talking about codes of sufficient symmetry achieve capacity. And this is a slightly grandiose title because the result is slightly more specific. Well, I only show you something for the binary erasure channel. Okay, so we'll be binary erasure channel. Okay, so the point will be the following. We'll look at we'll look at the codes. In particular, let me just mention, but it's not limited to what's called Reed-Muller codes. And so let me first explain to you what I mean that a code has sufficient symmetry. Something very simple. We have a code Cn, and you write down the code words. So x1n, and then have x21, x2n, and then you have x to the whatever, 2 to the nr, right? 1, and then x to the 2 nr n. Okay, so you write down all these code words in a gigantic table. And so maybe not ideal. I should have started with 0 and n minus 1, just slightly easier. Okay. So I'm just indexing the bits of the code word with this. So this thing here goes from 0. So the position goes from 0 to n minus 1. And so I will say that a code is one transitive, right? If for all, let's say I and j in 0 up to n minus 1, okay, there exists a permutation. So this is the set of permutations on 0 up to n minus 1. So there exists a permutation, right? Such that the following is true. First of all, the permutation maps I into j, right? So I'm taking a column, let's say I. I'm taking a column j. And this permutation maps I into j, no other restrictions, right? And then what I want is that I'm going to write pi of c is c. So what I mean is the following. If you apply this permutation on a code word, all I mean is that I'm switching, I'm applying it on the indices, right? And then by just notation here, okay, I'm just applying it to each of the code words. So if the code stays invariant under this permutation but can map I into j, right? Just means that the column I can be made to look like column j just by permuting the, think of just permuting the columns and then permuting the rows, and then you get exactly the same thing, okay? Sorry?
J gets mapped to I, or?
No restriction. It's just one condition, okay? So that's what's called one transitive. But if you want more, okay, and that's what we need, true transitive, right? Then you have if A unequal to C and B unequal to D, okay? So you want, let's say that, so for all A, B, C, D in, so if you now you can give me two conditions, right? Then pi of A should be, I guess, B, and pi of, okay, wait a second, I don't want the two, so maybe I wanted to have the B and the C not equal to D, and I want to go the A to C and pi of B to D. Okay, the only thing is I want that these are two conditions that you can actually fulfill, right? I mean, you cannot, of course, map 2 points to the same point or the same point to two different points. That's the only thing, okay? So now all it means is that I can now I now have two conditions, right? So I can say, for example, this should map to this, and for example, that this should map to this, right? Or this should map to this, and maybe this should map to this, okay? Just two conditions. And again, if for any such quadruples now that are consistent, I find a permutation that does it and the code is invariant, that's what I need, okay? So that's, so now in 1968, sorry, Kasami and Lin showed that, if you take standard Reed-Muller codes, they looked at the permutation group of such codes, so permutations that keep the code invariant. And in particular, what they showed is that Reed-Muller codes have a permutation group that includes the following. You take n log n times, so these are codes of size 2 to the n, so log, so if you take the log base 2 of the thing, that's an integer, okay? So you take an invertible matrix M of log size, right? And so, so any mapping of the following form will keep the code invariant. What do I mean? You can pick any invertible matrix like this, any shift, okay? And so what is now the B and the A? these are simply, these are vectors now of length log 2 of n. And you can think of that these are simply the numbers that, that index the bits from 0 to n minus 1, right? Right? I want to number these bits, and you can interpret that as a vector of length log 2 of n, right? And so if you number them like this, any such thing here, right? So this index goes to here, will keep the code invariant. Makes clear? And it's not very hard to see that this implies two transitivity, because you have basically 1 degree of freedom between these two by picking the m, and there can be many choices, and you have another 1 degree of freedom for the, that comes from the shift, okay? So you can now write, if I give you 2 pairs here that you need to fulfill, it's not very hard to see that you can do it by picking the m and the c, okay? And in general, there are many choices. Clear? Okay, so if that's not so clear, it just means that the code has that property, right? It's just a more explicit thing. Clear? Okay, so now we know that the code is highly transitive, and these are not the only codes that are highly transitive. No, this is stronger. This is stronger here. Okay, it just says this code has this and more, but it in particular has that property. This is, I think, the affine linear group, yeah, maybe Henri, right? Affine general linear group or something like that. Okay? Good? Yes?
Is that valid for generalized Reed-Muller code?
Sorry?
Is that valid for generalized Reed-Muller?
I think so, but Henri is the expert on that.
You do everything over GFQ.
Yeah.
The only thing the difference is you go to GF2 to GFQ, it's all the same.
Okay, and there are other codes too that fulfill, have this particular property. Okay, right. Okay. So now, fine. So what does this have to do now? So while the point is the following, we need one extra ingredient. This brings us back to basically the initial discussion that we had about thresholds, and remember, the initial discussion we had was about this Tillich-Seymour result, okay? But now we need a slightly different result. Again, it starts from this Rousseau inequality, but slightly different. And this says the following. If you pick, again, we have an omega, which is a subset of 0, 1 to the n. Again, we define this measure like this to be just the sum and of these measures here of the parts, and each of them is again this Bernoulli product measure, right? And so now this says the following: if this is monotone we saw already why this is good, right? Because if it's monotone, then we have this Friedgut, we have the Rousseau-Margulis inequality, and if this is symmetric. So there's one extra condition, right? Then, so if these two, then mu of epsilon of omega has a sharp threshold. And in particular, remember I had defined these epsilons here. In particular, if I'm looking at this, I can't remember, what is my notation? This delta, 1 minus delta. In particular, how far is this transition? Okay, so there's a constant, and then it's log 1 over 2 delta over log over n. Okay, so in particular, they show that if the omega is monotone and the omega is symmetric, so the only thing I have not explained to you, what does it mean it's symmetric? Well, omega is just a subset. So again, you can write down omega 1, omega 2, omega 3. So you can write down these vectors, right? In the same way as I wrote down here the vectors that correspond to the code word, right? So symmetric just means exactly this, one transitivity, right? Again, you have to write down here the columns, and there must exist a permutation for any ij that maps the I to a j and keeps the subset invariant, okay? So if these two conditions are true, then this has a sharp threshold. So the picture is again the one we had. And now, that is important. What is the transition with? It's not as good as what we had beforehand, okay? This is the log n, right? Beforehand, depending on the minimum distance, we might have been as good as 1 over square root of n, okay? Much, much better, right? It's 1 over log n, and then here also comes the, here I've explicitly mentioned what the this is just universal constant, but what the relationship is with respect to the delta, because this will come in important a little bit later. Yes?
So this is the implication of the Reed-Muller theorem?
That is the Reed-Muller theorem.
Well, Reed-Muller theorem says that there is a sharp transition provided that the property is not described by local structures and things like that. There's a condition.
No. So that guarantees that, right? Why? Remember in the standard Reed-Muller, okay, the standard result says that as soon as there's at least one component that has a decent, there's always at least one component has decent influence. Symmetry makes sure that all the components have the same symmetry, have the same influence, and hence that implies that.
Yeah, I was
okay?
thinking about.
Yeah. There are many. Yes. Okay. There are many different results.
And the window of the phase transition is indeed of inverse log n.
Right.
I see.
Okay, but there are many different, we're just taking one prepackaged result, and I'll mention something later on that Henri looked together with Santosh, a slightly more sophisticated version. Okay, there's a strengthened version by Bourgain and so on. When you have slightly more symmetry, you can actually get here a square, and this will come important, and that's, it's important in a second. I don't want to jump ahead. Okay, good. So now we're almost done, okay, because now we just need to string these things together. Right? So we take, let's say, our Reed-Muller code, right? And we take let's say, BC. And now what we do is the following, right? We look at this decoder, right? So we're looking at the xi hat map decoder. So we're looking at one particular position here. And we're looking at this particular decoder, right? So for this particular decoder, what it sees is an observation of length n minus 1, right? So now what we have is we're looking at 0, 1, not to the n, but to the n minus 1, because it only sees n minus 1 positions here, right? So now I can again define a subset omega, let me call it omega I, which is a subset of this. And what is the omega I? As before, and it's all the erasure patterns that cause this decoder to fail, right? So now I'm just looking at the ith bit of this, I do the optimum decoder ith bit. I cannot look at all the bits, but there's one bit I cannot look at. And as beforehand, I look at, again, because of linearity code, it doesn't matter which code rate I transmit, it only depends on the erasure patterns. So these are all the erasure patterns that cause trouble for decoding of the ith bit, okay? So now, what is the obvious thing that I want to do? Well, I want to apply this theorem here, right? So I need to check that it's monotone. And I need to check that it's symmetric. Right? Monotonicity is kind of clear, right? If I have an erasure pattern where I cannot decode the ith bit, I cannot do better by simply, again, hiding another bit from you, right? That would be nice, right? Just hide all the bits and then do better than not hiding the bits, right? That's pretty clear. It's not a formal proof, but, that's pretty obvious. Symmetry also is not very hard to see. Our code is too symmetric, right? Too transitive, okay? So, but remember, here we only need one transitivity. So why do we need two transitivity if here we have one transitivity? Why? Because when I'm looking at these code words that have length n, and I'm looking at a permutation and I'm looking at the ith bit, I need to make sure that the permutation keeps the ith bit the same. So this permutation has to map I into I, and then this, let's say, into here. Is that clear? Because I'm fixing the ith bit, and the omega I only consists of the rest of these bits here, right? So if I'm doing a permutation, I need to keep the ith bit fixed, and then the rest has to move. So the two transitivity will give me a one transitivity on the omega I, right? Okay, so hence, now we know that this decoder, so its error probability, if I'm looking now at the error probability of this, namely that this is not equal to the xi, that this is exactly now my function f of epsilon, right? This function is now simply the measure of that set here under epsilon, but we know that that's now fulfills the two conditions of Calais and thing. So hence we know that this function has a sharp threshold, okay? where sharpness here means 1 over log n log 1 over 2 delta. Right? That's the transition width. So if n becomes large, this becomes a jump function, right? It becomes a step function. But if this is a step function, right, we didn't just pick any function, we picked the exit function. That's the exit function. So we know that this is equal to the rate here, right? So hence we know where this position is, namely it's exactly at 1 minus thing, which is epsilon star, which is of course just capacity. Right? Okay, and that's how the proof goes, that's it. So, just maybe a few words, okay? So, first of all, this proves that the bit error probability goes to 0, right? Because we looked at a bit decoder, right? We looked at something slightly worse because I'm not allowed to look at the ith bit, but that only makes a difference with probability epsilon, which is a constant, a half or something, okay? So if this goes to 0, I mean, they go to 0 if and only if, right? But this is bit. Now, it's nicer if you have a block error probability going to 0, right? And so there's several ways of doing it. Henri and Santosh in the original paper had a very nice idea, and so we're coming back now to this, is that in case the code has slightly larger symmetry, then you can use a stronger result, which is called Bouguin-Calais, and then here you get actually a square, okay? And so why is that important? Well, what's the difference between a bit and block, right? At most, it's a factor n difference, right? I mean, by union bound, right? So if I can pick the delta to be less than 1 over n, right, then I'm fine. Unfortunately, in here, I can't pick it of order n because then these are of the same order, and I don't get a width here, right? If I just pick here something in that's n, then this and this will just cancel, and then I have constants, and I have no control anymore. Nothing goes to 0, right? But if I have here a square, right, then I can pick this to be n, and then that's one way to get rid of this thing. Okay, so if you can use stronger one, that's fine. There's another way that we have found more recently, and Marco had a lot to do with this, is that you can also use some bounds on the weight distribution. Okay, and one thing that I didn't say here, I should give credit to some other people, namely Abe, Spilker, and Avi Wittgensen. They have looked at exactly this problem, whether or not Reed-Muller codes achieve capacity. They have looked at different regimes, both for the BEC and the BSC, but their regime was where the epsilon in both cases either goes to 0 or goes to 1. Okay, so we are not looking at, or the rates, I should say. Well, both, doesn't matter, okay? But basically we're looking where the rates either go to 0 and 1. It's not a regime that in communication is super interesting, but for problems in computer science, that can still be an interesting regime, okay? And so they proved that in that sense, for the BC in both cases and for the BC in only one of the cases, I think if the rate goes to 0 here, that these codes achieve capacity. And they did it in terms of weight distribution. And if you kind of now use weight distribution, you can also relate bit and block, and even in the general case, and show that, if you can show just that the bit error probability in that sense goes to 0, the block also will have that, will also have this property. Okay?
Sorry, I just want to make sure I haven't missed anything. So earlier you promised this root n business, the root n thing. So,
the root n is only true for so the root n is unconditionally true if the minimum distance can scale like linear in the distance. So if you had now a code, which is not true, Reed-Muller codes only have minimum distance go like square root, okay? So if you could do that, you would get that very strong result, okay? But this, but for this you would need.
The proof of that root n in that case is something. It's not. It's a different proof.
So the proof for the root n. So we know that it has sharp threshold, but we have no idea where the transition is without these kind of tools. Yeah. So it uses similar techniques, not this Friedgut-Calais, but they do this. They start again with this inequality, the equality that I showed you, and then directly relate this to the minimum distance of the code. Okay. So their result is very nice because it's very general, but it doesn't say anything about the threshold, right? Similar, like you show some concentration result, like a zoomer or something like this, you can show that things concentrate, but you have no idea where around what it concentrates. It's the same kind of type of problem that you have with these kind of techniques. If you don't use the error theorem, but you use simply that it goes up sharply. You know that it has a sharp threshold, but you don't know where it is. Okay, so we combine this with the area theorem to show where the threshold actually is. Okay, so now, okay, that's pretty much, okay. I don't have anything to say. So for the general case, we don't know yet. As I said, the one relationship between the big and block is true in general. What is the difficulty to getting this done for the general case? Well, you can, the area theorem, you can still derive it. But as I said, this decoder here, the most natural decoder that corresponds to it, it's no longer clear that that is monotone. Okay? So you don't, so I mean, depending on how you think about it, it's not, here everything worked and there was no work whatsoever. I mean, you took 3 standard theorems, you just put them together, just click, okay, it just worked. But in general, it's not, not true. These things just don't quite fit. I mean, there's no reason to believe that this wouldn't be true and that similar techniques couldn't work, but we just don't know right now how to do it. And the same area theorem, as I said, you can apply to spatially coupled ones. I don't know, are you going to talk about that?
Yeah, it will come in.
Okay, so okay, so you saw a proof. So you saw a proof by Henri, right? Henri had this nice proof with the potential function, right? That shows simply what you can achieve in terms of the potential function. If you want to connect it now where this minimum of the potential function is, then you use exactly this area theorem to connect it to the map threshold of these codes, right? And if you want to know, for example, for a non-spatially coupled code, what their map threshold is, right? Then the idea is that you first go to the spatially coupled domain, just as a proof technique, right? You show that the map threshold for the coupled and uncoupled is the same. For the coupled one, you show that the iterative in the map is the same. You figure out what the iterative is. It turns out to be exactly this, area threshold, and that gives you then the threshold for the uncoupled system. Okay, so they're all kind of connected. Okay, so yeah.
What can you say about the iterativity code of LM codes?
Of Reed-Muller codes? Nothing. Okay, so you can, I mean, a lot of people have tried, right? Of course, there's all these symmetries, so they're very natural algorithms, right? Try with respect to all the orderings, for example, right? So what I didn't say is that these Reed-Muller codes are very much connected to polar codes. For polar codes, we have a successive decoding order. We can decode them. Now, Reed-Muller codes, you can think of all possible orderings that you have in there and try to do decoding according to successive, but there don't seem to be sufficiently many orders that actually has, I mean, for finite length this will help as other things help, but it doesn't seem to help asymptotically, okay? The natural thing, and that's also what we tried at least in the beginning a lot, of course, when trying to prove the Reed-Muller codes, is to connect them to polar codes, because that's the only new thing we thought that now people know, right, and it's very much connected. But so far we have no proof that connects it just to polar codes and then uses ideas about polar codes, okay? Okay, I hope the organizers don't ask for the money back if I'm ending early. Okay, thanks.